Okay, let's go ahead and keep going. We have our two tables. We can compare the numbers looking at the tables. Let's go ahead and do this next step that says, how do these look as recursive functions? So let's go ahead and do our green one first. So if we were looking at our green table for Calcurama, is this an arithmetic or a geometric sequence if we were going to write this as a sequence? What is it? You're right, it's an arithmetic sequence, and the reason we know that is because we're adding a constant difference. We're adding 0.5 million or $500,000 to each term. All right, so if we were going to write that as a recursive, we would say a sub n equals a sub n minus 1, meaning the previous term, plus 0.5 million, or if we wanted to write it completely, it would be $500,000. All right, so that's our recursive. Now let's go ahead and continue to look at our green Calcurama and come up with an explicit function, shall we? Let's do the explicit function. So the explicit function would look like this. A sub n equals our first term, and our first term we're going to actually say is year 1. We're not going to go with year 0 where we start. We're going to start with the first year. So the first year is 5.5 million. So we could write 5,500,000 plus our 500,000, which is our constant difference. I'm going to run out of space here. Times n minus 1. All right? And then if we wanted to write this as just a linear equation, how could we do that? Well, we would say, let's see, r of x, since that's our function, equals, and if we did all of our work here and we multiplied this out, we would end up with, let's see, we'd have 500,000 n minus 500,000. So then when we combined our like terms, we would have 500,000 n, or let's make it be x, shall we? Since that's what we're saying, plus 5 million, which is where we started. So 500,000 is our rate of change, our slope. X would be the number of years, and 5 million is where we start. So we've just written this 3 different ways, all representing the same function. Now let's take a look at our orange table, which is our Computafest table. All right, so this is going to be a little complicated, but I want you to follow closely. Let's start by first thinking about how we got each year, because we're going to have to figure out what our common ratio is. So we know, or I think we know, that this is a geometric sequence because we are multiplying each time. But the question is, what are we multiplying by? Your first reaction might be, well, we're multiplying by 15%, 0.15, but we actually are multiplying by something else, and I want to show you why we're multiplying by something else, because all we are doing when we multiply by 15% is figuring out how much we have to then add back to the original term. So let me show you what I mean. So here we have g sub n. Let's do the recursive first. G sub n is going to be the previous term, g sub n minus 1, times 0.15, which is our 15%, right? But after we do that, we're then going to add it to g sub n minus 1. So think about this again. This is how we're getting, this is the kind of the increase, all right? And then we're adding it to the previous term. All right? Now it's not arithmetic because the increase changes. If the increase had stayed the same, like in our first one at 500,000, then it would be arithmetic. But our increase is actually changing. Our increase goes up each time. So because we're multiplying by 15%. So let me show you something. Let's imagine that this is a number right here, and this is a number right here. And what we could do is we could use the distributive property backwards. Could we not divide both of these terms, g sub n minus 1, the previous term, times 15%? That's one term. And the second term, which is the previous term, g sub n minus 1. Could we not divide them both by whatever that previous term was? Could we factor out g sub n minus 1 here and g sub n minus 1 here and kind of do a backwards distributive property? So let me show you what I mean. G sub n equals g sub n minus 1 times, well, what do I multiply g sub n minus 1 by to get this g sub n minus 1 times 0.15? Well, I multiply it by 0.15. And what do I multiply if I was going to do the distributive property? What would I multiply g sub n minus 1 by to get g sub n minus 1? Well, I'd multiply it by 1. So now, if I use the distributive property, you can see this times this gives me this, and this times this gives me this. So all I've done is I've factored it out, and I've made a new a different version of my equation. Okay, I'm manipulating my numbers. So my recursive is really my previous term times 0.15 plus 1. And I could just combine those to 1.15. So if I multiply my previous term by 1.15, that will take care of that adding component that I have to add it to. Do you see what I'm saying? I'm not only taking the 15%, but I'm also taking the original amount. So it's the original amount and 15% gives me my new term. So my common ratio is 1.15%. or 1.15, all right? That's my common ratio. So g sub n is my previous term, g sub n minus 1, times my common ratio, which is 1.15. That's my recursive. Now, let's turn that into an explicit. And doing an explicit is a little trickier, but we can go ahead and say that g sub n is equal to my first term, which is 2,300,000, times my common ratio, which is 1.15 to the n minus 1 power. All right? And then what I end up doing is I break up this 1.15 times to the n minus 1 power, and that's really the same as, I'm going to keep this, 2,300,000 times 1.15 to the n power divided by 1.15, because 1.15 to the negative 1 power is just 1 over 1.15. So we've, this is a little phrase I have, cross the line, change the sign. Now, Then if I divide, if I do a little bit of simplifying, I can't really simplify 1.15 to the n power divided by 1.15. I'm just going to come back with n minus 1 power. But I could divide 2,300,000 by 1.15, and you can take out your calculator and see what you get. Divide 2,300,000 by 1.15, and what you'll end up with is G sub n equals what we originally started with, which was 2 million. Times 1.15 to the n power. All right? So what we've just done is we came up with our recursive formula. So this is our recursive formula here. Then we turned it into an explicit formula, which is right here. And now we've turned it into an exponential function, which is right there. All right? And the important thing about this, really the key thing about compound interest, is that it's the 1 point the interest rate. Okay, so you have to include that whole number 1 because that gives you the amount that you're going to be adding to it. All right? Now, how do these look as explicit functions? We did it. Which company will make more in the long run and when? That just requires us to do a little exploring. So let's start by picking 10 years. What happens after 10 years? And let's use our exponential function and let's not have this be G, that shouldn't be G of n. That should be P of x, and that should be an x there. All right? So let's go ahead and use these two functions, which are a little bit easier and simplified. So put in 10 for x for the Calcurama, and then put in 10 for x for Computafest and see what you come up with. Okay, so what did you come up with? Well, when I did it, I used this formula, and I did 500,000 times 10, and then I added 5 million, and I got $10 million. Then, go away, then I took P of 10, and I put in 1.15 to the 10th power, and I got 4.0 something or other, and then I multiplied that by 2 million, and I got $91,115.47. So I still, after 10 years, Calcurama is making more money. So then I kept going, and I'd like you to keep going and see if you find at what year does Computafest end up making more money than Calcurama. So what you should do is, it's pretty easy to do that, so go ahead and figure that out for Calcurama, and then find out how much it is for Computafest, and tell me at what year does Computafest make more money. So did you find that at year 13, R of 13 is $12 million. Is that right? Or is it 11,000,005? Now I can't remember. Let's do that really quickly. So we have, I need that to go away, 500,000 times 13 plus 5 million equals, 11,500. So let's go back here, and that is equal to 11 million, not 1,100, 11,500,000. All right. And then if we do P of 13, we take 1.15 to the 15th power